Okay, so we've so far found that when we have a force, we can calculate something called stress to determine how is that force going to affect just our average material. We're looking at a particular size, it's just on average for any cross section, how is it going to perform? And that stress causes a strain. Now, one thing we didn't show too much, we're going to get into it a little bit here, but I want to make sure that we talk about this now, is that we hit that tensile test, and we were to graph these against each other, what we would see in that tensile test is something like this. It would increase, and then it would kind of curve, and then finally fail. Now, we're not going to worry about this side over here too much yet. We'll get to that later. But the big thing I want to talk about is this section. It looks linear, and it is linear. And in this section, there's a nice little equation which is called Hooke's law. Because our stress is equal to our modulus of elasticity times strain. And this is species specific. We're going to get into where that comes from soon. What you see is that in this section, the amount of stress I apply is going to cause some proportional strain. So all the equations we're about to talk about only work in this nice linear section here, which is called the elastic region. Beyond that, things get wonky, we can't use this anymore. So stress is equal to modulus elasticity times strain. Okay, with that explained, now let's jump right into this. So I've got two equations here, and one is saying, well, what's my change in length? Well, that's going to be equal to this guy. What is that? Well, it's what's usually called the FLEA equation. Because it's saying, okay, I don't really care necessarily about what my strain is, I want to figure out what the change in length is. Sometimes that's more important. And so this just goes straight to the point. Now where does it come from? Well, you know that force over area is stress. So delta L is equal to stress L naught over modulus elasticity. Second thing you know is that delta L over L naught is equal to strain. And if I rearrange a little bit, I get stress is equal to modulus elasticity times strain. So this is just taking a few steps to get us an equation that's easy to use rather than having to realize all those equations in it, plug them together. Okay, now this second one introduces another value which you haven't seen before. This nu. It looks like a V, it's actually a nu. And that is what's called Poisson's ratio. What it says is that if I have, some strain in my lengthwise direction, well, there's also going to be a strain in the x direction, or the lateral direction, whatever you want to call it. And this Poisson's ratio says there's going to be a ratio of those two. There's going to be a ratio. And I did it in the wrong order. Always do. Or this is the d naught, like the diameter dimension, and this one is the length dimension. They should always come out positive because one of these is going to be negative and the other one is positive. And so this is how it's connecting together. We're using this to connect our strain equations, and through several steps we arrive at this equation right here. So this shows you where it comes from. You don't have to memorize where it comes from though. I don't want you to think that. Just make sure you're writing down these equations. So they are also given at the end of your chapter. Okay, now what do they show us? Well, they show us that our deflection or deformation, whatever, is dependent on material, geometric, and the loading parameters. All three are important. Also, we learned that materials with large elastic moduli deform less. That's always something that confuses people. You might think, okay, if I have a large modulus elasticity, I'm going to be very elastic because it's very large elasticity. It's not the case. Because remember, that's coming from that little curve. Stress is equal to modulus elasticity times strain. And the steeper this is, the less you deform under stress. And the slope of this curve is actually equal to E. So that's where we get it from. That slope right there, that is the modulus elasticity. And the steeper it is, the less you deform under stress. So it's actually less elastic. And that's kind of strange. Okay, another helpful one is figuring out the angle of twist in radians. Okay, always radians for a given system. So we apply some sort of moment. A moment is like a twisting force in a way. If you don't know what that is, it's also, you can also say like a force times a distance, or maybe refer to, like I said, a torque. There's lots of different ways of terming it, but whichever one of those makes sense to you, that's a moment. And another thing you don't know here is G. Just like we had that modulus elasticity, we also have G, which is our shear modulus. You can look that up for most materials. Okay, so that's it for this time. Thank you for listening, and I'll see you all later.